Welcome. Welcome. My name is Lu Li. I'm interim chair of the Department of Physics here. I'm so happy to see so many of you are coming here during the homecoming weekend. So this is the 30th year of Saturday morning physics. And we're having a wonderful series of lectures coming in this term and next terms. So without further delay, we will have my colleague Christine Aidala to introduce the program. Thank you.
Yes, good morning everyone here in the room at U of M on campus and to those following our live stream. And welcome to Saturday Morning Physics on this beautiful fall day. I'm Professor of Physics Christine Aidala, and I'm one of the organizers of Saturday Morning Physics, along with our team, including Carol Raybuck in the back, who many of you might have seen as you came in, manning the table, and along with Monica Wood and the staff of the Warren M. Smith Demo Lab. Before moving on to our program, I want to remind you that Saturday Morning Physics is made possible by you, thanks to your many generous contributions as Saturday Morning Physics fans. For more about supporting Saturday Morning Physics, go to saturdaymorningphysics.org. Saturday Morning Physics is also grateful to have the support of the Dr. Mary Lois Tiffany Endowment, the Hideko Tomozawa Endowment, the Van Loo Family Endowment, and the Pulikeshi Dayalu Astrophysics Fund. Before we move on to today's program, I'd like to bring to your attention a couple other public events that we have organized through the physics department this year. Just next Wednesday, October 8, we have our Ta-Yu Wu lecture by Professor Gabriela Gonzalez of Louisiana State University. The topic will be Einstein, gravitational waves, black holes, and other matters. You can find a flyer about that out in the lobby. We'll also be having a centennial celebrating 100 years of spin here at the University of Michigan. That'll be November 5th, an afternoon multi-hour event here on campus. So before moving on, I want to note that today's event will conclude with the traditional Saturday morning physics Q&A. For those joining us online, please send your questions to physics@umich.edu. This brings me to today's speaker, my colleague and many-year Saturday Morning Physics organizer, Professor Tim Chupp. He's going to be speaking about the science of baseball. Tim was born in Berkeley, California, and lived in Seattle, New Hampshire, and in Munich, Germany, before attending university and grad school. He was actually raised in a family of scientists, and I understand that he got to take apart a lot of gadgets when he was growing up. So it's unsurprising that he became an experimental physicist. He focuses on building instrumentation for measurements in elementary particle physics using atoms and nuclei. Some of his recent research includes measuring the anomalous magnetic moment of the muon, and he's currently spokesperson of an experiment to measure the electric dipole moment of the neutron, which probes forces that may have resulted in more matter than antimatter in the early universe. Yeah, he's been engaged with Saturday Morning Physics for many years. I'm new to the team this year myself. Tim is a distinguished fellow of the American Association for the Advancement of Science and of the American Physical Society. So please join me in welcoming Tim Chupp.
Well, thank you, Christine, and thanks everybody for that warm welcome. And welcome, it's great to see so many people here. You must be fans of baseball. This is quite a day, right? So we have, as I understand it, there's a football game today and a baseball game later on. So lower left is right after the last pitch. What day was it? So it was Wednesday, I believe, or Tuesday. Anyway, earlier this week, and the Tigers are playing today at 8 p.m. In Seattle. And as Christine mentioned, that's one of the places that I lived when I was growing up. So baseball isn't just played at the major league level, of course, and baseball or softball are played there's t-ball, right? So for many people, it starts there. Not for me. I had to put on a helmet and learn to swing a bat in Little League. And I've forgotten that by now. I just want you all to know. Softball, this in the middle, international, that's in Australia. There's a significant baseball in Australia. That's Adelaide against Canberra, by the way. What are they called? Well, I forgot, but I can't read it. And then in the upper right, there is a women's professional baseball league starting up in March 2026 of women fast pitch regular baseball. So lots of people play the game, but some of the best examples, and certainly some of the best pictures and videos that I have are to show you as examples of the science of baseball are from Major League Baseball. So we're going to talk about physics in baseball. We're going to ask you to take part here in the room in a significant number of activities here today. Some of them are kind of like quizzes, and some of them are actually things that you get to do. So I did want to note that the science of baseball is a scholarly endeavor. There are many, many papers published on various aspects of the game, the science, the physiology, the neuroscience, etc. So here's just a sampling of papers: the dynamics of the baseball bat collision, corked bats catching fly balls, the motion of arbitrarily rotating. I'll just keep going. Spin. All right, you get the point. Okay, so can we start with a quiz? Sure, you ready? All right, what forces matter most in baseball? And let's see, I could probably see anybody who raises their hand. Just name one. Yes? Velocity, okay. Velocity is, to a physicist, not a force, but it is certainly a quantity, a physical quantity that matters quite a lot. A force is a push or a pull, is the way I define it in introductory physics. Yes?
Gravity.
Gravity, yeah, gravity matters a lot. It matters in everything we do here on Earth. Other? Yes? Friction, yeah, friction. In particular, the friction, actually there's a number of frictions, like a runner wouldn't be able to run without the friction between the feet and the ground, but maybe very important for us today is the friction of I know what you're thinking, air friction or air resistance, aerodynamics and aerodynamic forces. Yes, any others? Yes? Torque. Okay, torque, actually, we will consider torque a force today. It's a force that causes rotation, so it's a push or a pull that makes rotation in essence. So torque is very good. Okay, any others? One more? Yes, one more. Yes, right, the rotational force or torque. Okay, good. Okay, so here's my list. Gravity, good. Friction, good. Not even in the right order. Viscosity, which is a force which is related to air resistance, right? So it's a kind of friction, as we said. Ooh, elasticity, right? What's elasticity? Things stretch or compress or bend and spring back, okay, etc. All right, so this is the baseball field. There's just a couple of interesting things about it. You may or may not know, but it should be fairly well known that it's 90 feet along the baselines. If you draw a straight line from first base to third base, it does not go through the pitcher's mound. Surprising, but the 60 feet 6 inches, many people have heard of as well, and there is historical lore about that, whether it is somewhere in the Bible or that would be the Old Testament, of course, etc. At any rate, that 60 feet is really important. So what we're going to start with is this problem. I called it a homework problem, but it's yet another challenge for you here. At least I want you to think about whether or not you could do this. So that's Tarek Skubal, just the other day, throwing a 100-mile-an-hour pitch, which he did many, many times, 14 strikeouts. And I want you to notice in the upper right picture how far in front of that 60 feet 6 inch marker, the rubber, on the mound, is from the plate. I also wanted to just note, this is really kind of interesting. I have to admit that, as noted, I grew up in New Hampshire, which is New England, which is Boston Red Sox nation. And Ardolis Chapman, I was kind of surprised to learn, because he was a Yankee nemesis, has been pitching for the Red Sox and did an amazing job on his closing out the one game that the Red Sox won in that series. He has thrown the fastest pitches ever. Now, when I say the speed of a pitch, that is the speed with which it leaves the pitcher's hand as the maximum speed as measured by a radar gun, the thing that the cops use to measure speed of a car, and of course it measures the maximum speed, right? Not when you slowed down, right? When you noticed the cop or whatever it was. Okay, and some of those, those pitches were a while ago, but he was throwing 101, 102, 103 earlier this week. What does that look like coming at you? Whoa. Okay. And we can do it. Don't blink. That's really something. Imagine being that batter with that slider going the other way, sliding the other way. Not a slider. Okay, so here's the problem. How long does it take? Why 55 feet? Because the ball leaves the pitcher's hand significantly in front of the 60-foot rubber on the mound, so we'll use 55 feet. We use 100 miles an hour, which is 147 feet per second. How long does that take? At least, how would you figure that out? Right? Think about that for a second. I'll give you a big hint. You would divide the distance by the velocity, right? The longer the distance, the longer it takes. The larger the velocity, the less time it takes. So divide the distance by the speed or the velocity. 55 divided by 147 is 0.37 seconds or 370 milliseconds, which is a good unit to use in baseball. Things fall, however, for question 2, excuse me, how far does it drop? It's called drop, okay? Well, naively, if only the force of gravity were involved, then the bottom equation, that the change in height is this thing we call G, which is how fast gravity pulls on things, how hard gravity pulls. It's called the magnitude of the gravitational field, or many people learn to call it the acceleration of gravity, and it is an acceleration. Anyway, I did the math for you. It should fall about 2/3 of a meter or 2.2 feet. T is the time, excuse me, yes. T is the time. Very good. Yeah, this is kind of advanced, but not for this crowd, I know, for sure. But nevertheless. Okay, so the thing about falling and getting to the plate is going to the plate is a horizontal motion. Falling is a vertical motion. And what we learn and what we teach, at least in the simplest approach, which is sometimes effective. Thank you, Monica, for setting this up for me. I would never do it right. What we learn is that the vertical motion and the horizontal motion are separate. So this demonstration is going to drop a ball, the white one, and propel a ball forward, but of course it's also going to drop, right? And I think you can kind of anticipate what the trajectory of this is. I'll tell you that gravity is by far the most important force in what I'm about to demonstrate. And the evidence is going to come to you through your ears. You're going to hear the balls, each one separately, hit the ground or the floor, all right? So I only get to do it once, right? So here we go. And then you count down, right? This is traditional here. 3, 2, 1. It's just indiscernibly simultaneous. It's not simultaneous. Indiscernibly, that's a double negative, the in part. Indiscernibly not simultaneous. That means as far as you could tell, it was simultaneous. This is a science talk, not a language talk, but nevertheless. Okay. Right. So there's our answer. But it's too simple. We've left out many of those forces. In particular, we've left out the frictional force, or the viscosity, or the air resistance. So that causes the ball to slow down as it's moving towards the plate from the pitcher's hand by about 10 miles an hour for a 100-mile-an-hour pitch, 9 or 10 miles an hour. So when it gets to the batter, it's maybe 90, 91 miles per hour when it crosses the plate or hits the bat. The other thing is that pitchers learn how to grip the ball and release the ball with their arm moving in a way that induces spin on the ball. Spin around some axis, a spinning ball. And I will show you some calculations, video calculations of spins of different pitches. But the axis of spin is clear, right? It's spinning around the axis, like the Earth is spinning around its axis. The ball is spinning around an axis, and the angle of that axis is controlled by the pitcher and the way the pitch is performed and released. So it's spinning, and the spinning causes aerodynamic forces, which we'll talk about, and also the spinning changes. It slows down as well. Right? And so that affects how far it falls as well as how long it takes to get to the plate. So we're going to look at pitching here. Here's a pitch, I think. Okay, do you see Whitey's swing? That comes later. That question comes later. We'll talk about that. But nevertheless, I think I can do it again. Right? Shoom. It just unexpectedly moved. That is to say, it moved in unexpected ways, and that's what pitchers do. They try to fool the batter with a pitch that looks like it's going to do one thing and it does quite another. And of course, it's only doing that because of the forces on the baseball once it leaves the pitcher's hand and before it hits the bat, if it does. What makes that happen? Well, I'm going to talk about the aerodynamic force in a bit of a detailed way here. So here we have a ball moving to the right. Okay, the pitcher has released the ball. As far as the ball is concerned, there's a wind blowing past it, right? Okay, just like the dog with its ears, the dog puts its head out the window of the car, and you can tell that there's a wind blowing past because of the dog's ears, right? Or whatever it is. But as far as the ball is concerned, there's a wind blowing past it, and that wind slows it down. That's drag. Okay, we call that drag. That's a force. There's gravity, of course, that we mentioned. And generally, the ball is spinning. So this particular ball will be a fastball, which is released in a way that essentially the axis of spin is horizontal, the ball is spinning backwards. It's called backspin. There's a little bit of air that goes with the spin of the ball, sometimes called a boundary layer. And the consequence of that is that there's a different speed of the air over the top of the ball and the bottom of the ball. And if you look, the backspin and the air in the top is going in the same direction, so that's faster. And on the bottom, it's going in opposite directions, so that's slower. And when there's more pressure below than above, there's lift. I think I have a picture of that. Right? Wind speed at the top is greater than wind speed at the bottom, and that causes lift. So fastball does not fall the way this ball did, right? Because it has an extra force upward as well as a drag slowing it down, and that's lift. Does that make sense? Right? We get all these forces. So the things on the right are arrows. Actually, everything's an arrow here, including the spin. But what we, in physics, we call any physical quantity that has a direction a vector. Okay, I don't think I'll use that term again, but I wanted to make that note. Now, the drag does depend on the velocity. So I have this graph. I've used this graph in previous talks, and I didn't refresh it very much. But basically, the bottom axis of the graph is velocity. And the only point is that the drag on the baseball is not constant as the baseball changes its motion, as it slows down and its spin changes. Okay. This also is kind of interesting. There are different pitches, and there's different spin rates. A fastball is spinning backspin, so that's why it's negative, 95, 90 mile an hour fastball. Sliders are released in, I'm left-handed, okay, so you'll see this here, are released in a way that they spin around a different axis, and that's considered positive. And then this thing called induced vertical drop is a technical term, and when that number is negative, that means that the ball doesn't drop as much. So fastball doesn't go as much as gravity alone would cause, and these other pitches tend to drop more. Okay, so why did the bottom drop out of that pitch? Right, because it was a kind of pitch that had a positive spin-induced vertical drop. And then it's all in the grip, kind of, not just. But here's several grips. I thought this was kind of cool. That's one way that the pitcher controls the spin of the ball. And another way is the arm motion. I know it's kind of painful, isn't it? Okay. Now, you don't want to see that again, right? And why do they get injured? You might wonder. The physiology of baseball would be a whole different thing, and the sports medicine. Okay, so scientists, engineers, and physicists in particular use a computer technique that, especially with powerful computers that we have now that are very, very useful for studying a lot of phenomena and predicting a lot of phenomena, designing a lot of things, airplanes, cars, chemical reactors, etc. And this is called finite element modeling. The finite elements are steps in time, for example, in this particular case. And also the space. So this actually is a fairly complete model. This is a calculation. A model by one of the main companies that that develops some of the software for finite element modeling, FEM, and applications. And let's see what it looks like. So first of all, you can tell that that's a fastball, right? Because it has backspin. It also says fastball at the top. Additionally, maybe you can tell, it's a little hard to discern, that the spin is changing ever so slightly. Okay, so the spin and the speed slowing down. It's a little hard to tell. Let me show you a few other pitches. Okay, that slider, I think, is next. So the curveball. So the axis of spin is different, and therefore the aerodynamic force is different, clearly causes the ball to curve towards your right. Right? Okay, and then the slider. This one's pretty amazing. You see how the axis is now completely vertical? And that causes the aerodynamic force to be completely horizontal, and it moves more. So this is what a computer can do to illustrate that, or in this case, the company is illustrating the power of its software, but that's really cool. All right, every sport that I've thought about that uses a round ball that has the chance of spinning has the same science. So I've given a Saturday morning physics talk on the physics of basketball, and the soft touch when a basketball leaves the player's hand with backspin it gets a little extra lift, and it follows a trajectory that's not a simple gravitationally driven trajectory. This is, oops. Oh, well, I may not be able to play that. Let me see. But in soccer, oh, there. This is Beckham, famous for maybe a fail. Sorry. Well, or Federer. Okay, let me just note, these are suddenly not working. But, okay, in soccer, maybe you've seen how, it's particularly on free kicks, the ball bends, that's called bending. In tennis, hitting a ball from like this height over a net at that height as fast as possible would cause the ball to go way past the end line if it didn't have topspin. Topspin, backspin makes lift, topspin drives the ball down, so that's why they can hit the ball at 100 and something miles an hour, and it does not go way over the end line. Okay? Simple gravitationally driven trajectories would. So that's the reason for topspin. Okay, all tennis players are taught that at some point, probably fairly early in their tennis careers. But they should be taught the physics as well, don't you think? Okay. So we're doing great. Okay, let's. I like this one. I searched for a lot of Tigers videos, and if they're destroying the Yankees, I love it. Okay. So, yeah, so what is he thinking? As the same question I had earlier. Why swing at that pitch? Okay. Yes? He's not thinking. He probably doesn't have the time to think, right? Yeah, remember the 307, sorry? He's reacting. And this is my job, so. Yeah, it's his job to react. Okay,
I said because the pitcher, his job is to make a strike look like a ball or a ball look like a strike. The hitter sees up until 55 feet, the ball looks like a strike. Once that last 5 feet happens and the ball moves, that's the result that you get right there. So the hitter's job is to hit what he sees. See ball, hit ball. It's a strike up until it moves. And that's why he did that. So he's not thinking. He's just reacting. That's all it is.
Yeah. I'm going to repeat that for the online listeners, and I'm just going to summarize it as see ball, hit ball, right? And that's absolutely right. Okay, so I'd also like to sub-summarize it as he's actually not thinking, as you said. He's reacting to the pitch in a way that he's learned over a long time. But that's not the physics of what's going on, or the science of what's going on, which is mostly why we're here today. Saturday Morning Physics is to educate, but also to entertain, excite, and engage you. So hopefully that's what we're doing throughout this presentation. Okay, so I want to go through this so that you understand the time. We already estimated the 370, let's say 400 milliseconds, 4/10 of a second, that it takes a fastball. So here we are at the start of the pitch. You can see that the pitcher's motion takes at least 6/10 of a second from the start. The pitch clocks are what, 15 seconds now? 7/10 of the second, the ball is just leaving the pitcher's hand. You can't really tell from this center field camera angle. The pitch is pretty much, it's moving away. from us. So we can't tell how far it is, but I can tell you it's later, so it's closer to the plate. And between 0.8, in that tenth of a second, it's moved almost a foot, right? And another tenth of a second, a little bit less. And then is the swing. So remember, the pitch left at 0.7 seconds, and the swing is about 1.1 seconds. So that's the 4/10 of a second, or 400 milliseconds, that's going on here. And of course, he misses it. So this is, yes, he's reacting. And the real question is, how long does it take to react? And there are some things that are physiological about this, and I think it would be really interesting. So what we like to do here at Saturday Morning Physics is engage the audience. So we've got a job for you, which is to help measure your reaction time. And to do this, we are handing out yardsticks. This will take a minute. We need kind of one for every pair of people because it takes 2 people to measure one person's reaction time. And you also have to stand up. Should we turn the lights on? Preset 1, try that. That doesn't work. Okay. So, you can help me. No, all right. Christine, would you help me? All right, here's what we're going to do. Okay? So I learned this because, like, what seemed to be a rich uncle had a dollar bill, and he had me do this with my fingers, and then drop the dollar bill and had me try to catch it. And if I could catch it, I could keep it. So I had to learn how to get cues from my uncle to tell when he was just going to wink a little bit, and I got rich. At least for a 5-year-old. So if you put your fingers around the 20 inches, okay, so one person will hold the ruler, the other person will have their fingers at 20 inches. And without any cues whatsoever, the person holding the ruler will release it, and the other person will catch it as quickly as possible in the 2 fingers. Does that make sense? Watch. We'll do it once. Okay. And then you look where she caught this, which is at 6 inches. Right? So it dropped 6 inches. You want to know that distance. Practice. And then do it. Let's see if you can do that again. Yeah. You're very good. You're very quick. Thanks. Sure. Eight. Same. Age.
You're done with me?
Yeah, thanks. Make sure that both people get to do it, right? Two fingers. Yeah. You ready?
I didn't mean to be cross.
Here, you can do it. 20. Great. 30. That was 11. One more time.
Which one?
About the same. 30, 10. So 10 is your, don't remember that number, 10. Okay. All right. Recess is over. Just pass them to the side. I didn't mention this because you were having so much fun, but I hope you remembered your number, right? How much you went from 20. So if it went from 20 to 28, which is mine, that's 8 inches, right? It dropped. Yeah. So I illustrated this with Christine with this one, right? Everybody had yardsticks. This is a meter stick. Science usually does things in meters and so on, kilograms and all of that. But we're using inches. It's just fine. But you might wonder why we didn't do that. Well, these are much more expensive. It's tariffs or something. And the other thing is that, as you all know, baseball is a game of inches. So, keep my day job. That got a better laugh than... It is a game of inches. Okay, we can do it either way. We just have to know G. Remember that? 1/2 GT squared. You don't have to remember it, but that's the same T. That's the time. But now we're going to find the time knowing the distance. And in this case, aerodynamic forces don't matter. So here's a chart. Okay, so 8 inches. I was very impressed with Christine, which was 6, right? Which was 177 milliseconds. I'm at 204, which is, but anyway. So what I want to do, this is it's a little risky of me, but I'm going to try to estimate. Here's a real science as we work. Okay, so this is a previous group of data, but I'm going to actually try to enter in a very rough way, and maybe Christine can help me kind of estimate or count how many people were in each of these intervals, right? So if you were between 0 and 2 seconds, raise your hands. Huh? 0 and 2 inches, I'm sorry, 0 and 2 inches. 0 and 2 seconds, goodness gracious. 0 and 2 inches. Okay, 1. Okay, that's extremely impressive. All right, so number 1. Okay, I had 1 between 2 and 4. 1, 2, 3, 4, 5, 6, 7. Okay, it's going to get harder, but all right, 7. Okay, how many more? 10. All right. I'm going to let you tell me because I'm just trying to go quickly here. Between 4 and 6? $26 or $30, which is $28, yes. And between 6 and 8? Similar. $42, that's the answer, okay. And 8 and 10? That's where I was. I can tell my age. Uh, 10 and 12? It's going to start to go down. Is that 1? I know there are at least 2. Okay, and any more than 12? Which, okay, so I'll just go through it. 12 to 14? 0. 14 to 16? 16 to 18? 1. And, oh my goodness. That's a surprise for the end of the talk. And 18 through 20? Okay, good. So this kind of graph is called a histogram. It's a good way to show a distribution. And there always is a distribution. This is a population, and we're measuring a quantity within the population, and there's variation that has to do with a number of things. It probably, if we were to do a careful study, would have some age correlation to it. I know the very shortest one was a younger member of the audience. I'm one of the older members of in the room, and I was at the longer end. And I can also tell you what the average is, which is way down here. It was 180 or 181 milliseconds is the average in the room. So let's go back and keep that in mind. And then you'll know whether you're above average or below average. And the thing about being above average or below average in this case is if the time is shorter, then you're below average. And if the distance is longer, then you're above average. So if you think about it, that means everybody's above average. So, all right. Here's the thing. What goes into that reaction time? And let me go back to full screen. This is simple. This is a physicist version of it, and it's pretty amazing how neuroscientists respond to my doing this. But definitely, we're using our eyes to determine when the thing starts to drop, right? So that is some kind of visual response. It takes some time for us to process that or react. And this is something that you haven't had much time to learn, right? I bet you if we did this all day, you would be bored, but also get better at it. And muscle strength is also an issue, like, because you have to close your fingers it takes muscles to do that. So we don't necessarily think of that as a measure of strength when we go to the weight room. I don't do this one very much, but it's still, it's the same issue, that we're trying to get our fingers to move fast enough to grab that thing. All right, but we can measure this. The visual response is, we'll measure fairly rapidly. Maybe you can help me with this. I just turn it on? Okay, and we have to make the room a little bit darker. And I have to hit B on my computer. So we have a blinking light. And I wonder if the video people could indulge us too. But you can tell it's blinking, right? If you could just turn those out for a sec, Carl, that would be great. Okay, that's probably good. So you can tell it's blinking, frequencies on the... Okay, now that's blinking faster. Okay, that's 2 times a second. 3, 4. There's a point at which I want you to tell me that it's become a blur. I cannot distinguish and process that these are separate flashes of light. Just raise your hand and I'll stop when I get to half the room. Okay, that's about half the room. And for the rest of you, how about that? That's like a steady light and slowing it down again. Okay, that wasn't, okay, great. All right, so about half of you had your hands up, at 30 times per second, exactly, 30 times per second, that is actually the rate at which most normal televisions refresh because of our visual response. It doesn't need to be faster, except for like gaming and stuff like that. Thanks. So that's 30 milliseconds. The brain to finger, I just have to tell you that skeletal muscles, the nerves travel at 100 meters per second. It's about, this is why I brought the meter stick. You know, it's about a meter. But the math is easy, right? That's 1/100th of a second, or 10 milliseconds. And the rest of the, in this case, 190 I use for this example, has to be the muscle strength part, right? So the stronger, and I think that the first two are pretty common, all right? At least it's not going to be much less than 25 or much more than 35 from what I saw people raising their hands. And of course the skeletal muscle one, okay, smaller people, maybe it's a little faster, but anyway, the 150 is the muscle strength. And just so you know, that's reaction time is largely about strength. It kind of makes sense, right? The people who are better hitters in baseball are characteristically have more strength, are stronger. And by the way, if you want to do this at home and measure your muscle strength, it takes a little practice, but you just do this as fast as you can and maybe see how many you can do in a second. So you need somebody with or look at a stopwatch, or see how long it takes you to do 20 times. And our cell phone stopwatches are really good for that particular experiment. So that's the reaction time part. So that's a really important component of hitting. Does anybody know who that is? Jackie Robinson. So you can see the 42 in the bottom right, kind of. Yeah, Jackie Robinson, great hitter, great pioneer of the integration of baseball, and a beautiful athlete as well. So what's happening when a ball is batted? And well, we're going to start with a simplest model. There is an approach to understanding complex phenomenon with physics that I call effective physics. We make it as complicated as we need to figure out what's going on. And I like that term, so effective physics. So here is the simplest way of thinking about what happens. The bat is heavy. The ball is significantly lighter. And when the bat hits the ball, let's just start by modeling it as, well, let's see. I'll show you this, which is called an elastic collision with a very heavy object. You got that? So at the beginning of the Saturday morning physics jingle, it's coming up, there we go. There's a set of balls that do this, and they all have the same mass, and they're steel, and there's very little energy lost when one hits another. And so I am raising the one on your right, and it's going to come down and hit this stack and transfer energy and momentum, two physical quantities, to the stack of balls. And it's going to only transfer as much energy and momentum as the ball that swings in has. So for the most part, a little bit imperfect because it's effective physics to do what I said. For the most part, the ball that recoils with the same velocity as the ball that comes in. In a perfectly elastic collision, that would be the case. So basically, we call this a brick wall collision. The pitch ball comes in and it hits this heavy thing, the brick wall, and it bounces back with the same speed, but in the opposite direction. So we put a minus sign, and the arrow over the top means it's got a direction. However, the brick wall is the bat. And when the bat hits the ball, it's moving. And there's the speed of the bat. So we have to take that whole brick wall picture and we say boost, okay? We have to make it move at the speed of the bat when it hits the ball, which actually turns out to be 70 to 80 miles an hour mostly. So go forward, please. Yeah, oh, there. Yeah, anyway, so there's a little bit of math. And the velocity of the ball after it's hit, just as the bat hits it and leaves the bat, is called the exit velocity. And in this simple picture, where there's no energy lost in the bat-ball collision, the velocity after, that's the bottom one, plus the velocity of the bat, both to the left, become the velocity of the ball, the exit ball, in the stadium, which physicists sometimes call the lab frame. So it's a moving frame, lab frame, and the whole process developed initially by Galileo is called relativity, actually, when we ask what happens in one frame of reference changes to another, okay? So here's a picture. It's all about bat speed, right? The pitch is 90, 100 miles an hour, maybe as low as 80, but then the bat is moving at 80 miles an hour, so you add those two together in the best of things. But is the collision, that's what happens, elastic or inelastic? How much energy is lost to the ball, we'll start with, but then we'll have to consider the ball and the bat itself, right? Because some energy goes into the bat. And that energy has to appear in some other form of energy, and I'll tell you that it's heat. So if you do this experiment many times, and we've done that here in this, in Saturday Morning Physics, with a different kind of ball, the ball heats up. We did it with a basketball, Monica and I. So I'm going to quickly show you the ball, how elastic the ball collision is. So I have a steel ball like the ones I showed you with the swinging balls, and I'm going to drop it, and I want you to notice, it's dropped from 100%. I want you to notice about how high it goes, okay? So every bounce it loses a little bit. So there's some inelasticity, there's some energy that's of the mechanical motion, the motion, energy of motion that's being lost. But that's actually fairly good. Golf ball, I'm just going to do a few. Not quite as good, and they're gonna go everywhere. This is the 8 ball. I'm behind you anyway. This is kind of cool too. All right, we better get to a baseball, right? Okay, so what do you think? This is a fairly standard baseball. 50? Not great at all. Right, okay. So that is called the coefficient of restitution, how much of the initial energy is recovered. The height is proportional to the energy. The difference in height from 100% is the amount of energy, proportional to the amount of energy lost. So going through it, baseball, about 1/3 of the energy is retained. 2/3 of the energy in the ball-bat collision is lost. So we need a, by the way, that's actually been measured in the laboratory with this device. I think that's kind of cool. That says 50 to 55%. So it just gets more complicated. So to make the physics effective enough to include the energy lost, the inelastic losses of energy, we just have to take account of that. Okay? So a lot of this kind of science of physics is accounting, really, and doing the math of the accounting. Anyway, the bottom is momentum, that's what P is. The top is the energy, and we have to account for the lost energy, which is the very last quantity. E is for energy, LOS, S is for loss. Okay. So that is a really excellent ball-bat contact. This is Shohei, and he's hitting a... Okay, so come on. Okay. There's a video here, but it's just beautiful. That's why I played it. Right. And then up on the screen of the TV broadcast, this appears. All right? Exit velo. Velo for velocity. So exit velocity. So we're going to talk about that. This is a new, relatively new, like in the past decade or so, quantity that has entered the lexicon of sportscasters, broadcasting and commenting on baseball games. So this is data about the ball leaving the bat at 117.7 miles per hour with a launch angle of 21 degrees and the distance it went over the fence, I think in Dodger Stadium. So we're going to talk about the effective physics of exit velocity. So this is maybe fairly not surprising. The line, the arc of the line shows what happens if, I have to say, the horizontal axis is distance from the plate. And this is from the third base perspective. So the ball is going to the left, and then the vertical axis is the height of the ball. So that shows what we call a trajectory. Okay. And that would be a trajectory where only gravity affects the ball's motion after it leaves. And there's some math there, but that doesn't matter. It's 600 feet in the horizontal and 80 feet in the vertical, so that doesn't look like 21 degrees, but it is. And the distance it would go with no air or other real reality of the ball bat encounter would be about 560 feet, okay, which is, I don't know what the longest home run ever is, but it's probably about that. Right. So what's missing, you've seen this picture before, except it's rotated by 21 degrees. So now the aerodynamic, the drag, is opposite the motion. The lift for a ball hit with backspin, right? It gets extra lift, if you remember that. And that's what's missing. So this is, I'm going to skip over this, which is also science, but so is this. So putting all of the science into the ball leaving the bat with an exit velocity and a launch angle, this is actually on my computer. I did this calculation. I'm going to show you the result. This is a spreadsheet. These are used in science as well, as checkbook balancing and things like that, accounting. And it just tells us everything about the ball as it's moving. And this particular problem I set up had a backspin of 1,200 RPM. It's in the white on the left, etc. And this is the result. Okay, the red. So the black curve is what I showed you before. No aerodynamics of a spinning ball with drag. And the one on the right shows you. Sorry, the red one shows you the actual calculated path of the ball. Okay, well, okay, left or right, take a look at left or right. Can the online people see that? Oh, there, it's back. All right, so my question to you, real quickly, is why is this actually going higher for part of its trajectory than it would if there were only gravity pulling it down? Right? And that's the backspin, exactly. Right? So, yeah, what a drag. Okay, this is a quick story about exit velocity because exit velocity started appearing in 2015. Tim Rohan was a University of Michigan Daily sports reporter who went to work for the New York Times, which had a sports department at the time, and he wrote an article, The New Way to Judge Hitters. It's rocket science, sort of. So I'm not gonna read the whole thing to you, but I wanted you to know that various people were quoted in this article, including me, and the general manager of the Mariners said, Okay, so the Tigers are playing the Mariners today. You don't have to be a rocket scientist to see that if you hear the sound of the ball off the bat, that's all you need to know. I'm not a rocket scientist either, but I'm a nuclear physicist. It also said I was a Boston Red Sox fan, but I seem to remove that. This was a phone interview, and I said, well, you know, the bat is moving at 80 miles per hour, hits the ball in just the right place. It's undercut, so it gets a little bit of backspin. We now all know all about that. And the pitch is moving in crazy ways that we've seen, so the batter has to make micro adjustments if the batter is going to successfully hit the ball, little small adjustments, faster than the speed of thought. I thought that was a great term. And yeah. The copy editor of the article changed that to faster than the speed of light. So be careful whom, right. And then there was an erratum, you know, because it was even in the print paper. We're running out of time, so I'm going to quickly go through the sweet spot. The sweet spot is certainly where that ball-bat collision is taking place. In this case, it's in a place where a lot of energy goes into something other than the ball. It goes into the vibrations of the bat. And that's easy for you to discern. Okay? So here's a normal bat. I'm going to hit the bat with a ball at a few different places, and we actually have an electronic device here that measures the vibrations of the bat, and I'm gonna, we have to listen. So I'm gonna go towards the end of the bat. Can you hear that? And then towards where that picture is taking place. And then at the sweet spot. It's really quite different. And then, do I have to hit it harder? All right, so what we're showing here is actually the vibrations as time. Okay, bad spot. Geez, another bad spot. No, it's not working very well. Sweet spot. So there's a lot of vibration. There's a lot of vibration. Much less. So that shows, again, that we're conserving energy for the ball-bat collision. Now, about bats, there's all sorts of cool things about understanding the bats. If you hit them in the sweet spot, you're hitting it at the place where all these are called modes cross, and very little energy can go into the vibration of the bat. This is startling. Okay, so that can happen as well. All right, I want to talk about the torpedo bat. This is Aaron Leonhardt. Aaron was a professor here at the University of Michigan. Prior to that, a few career steps prior to that, he was a undergraduate student here at the university. We had hoped he could come to give this lecture today. Instead, he's going to join us on Zoom for the question and answer period. I wanted you to know. But Aaron is most famous lately beyond baseball, where he's developing an amazing career and has just been named the manager of Arizona Fall League team. So it's his first management job. And I think he's listening. Developed something called the torpedo bat. Who'd heard of the torpedo bat? That's one of the really amazing things. Yeah. So I think it's fair to say that the torpedo bat is still around, but it made quite a splash at the start of the season when the Yankees hit a large number of home runs using this new kind of bat. And Aaron had worked for the Yankees. He's now working for the Marlins organization. Cal Raleigh is a switch hitter. He ran the home run derby, as I understand it, with a torpedo bat, and he hit 60 home runs this year as the home run leader of the year, just as some evidence. And I want to show you this picture of the torpedo bat, which is at the top, and the regular bat, which is at the bottom. And we got a torpedo bat. We're not going to do any science with it right now, but I'm going to just show it to you. I'm not going to do that, actually. Oh, okay, I can hold both, thanks. Right, okay. And try to make it look like I know how to swing a bat, which I'm not going to do, but I do want to just kind of point out, as you can see maybe almost better in the picture, that the regular bat just tapers outward the whole way to the end. And the torpedo bat is fatter and then becomes thinner. So there are a number of consequences of that. The Louisville Slugger, which provided this one for us, or Raleigh did, I guess. But the Louisville Slugger people, are trying to sell these bats. But what I want to tell you is, in order to swing a bat, it takes strength. That's the strength we measure in the reaction time thing. It takes strength, and you want to get the bat moving the fastest. You want the ball to hit the sweet spot. So the most forgiving sweet spots are a little bit bigger. And also, this bat has less resistance to rotation. This is rotation, which is called moment of inertia. So this is a really long bat, so I'm really choking up. But so there are a number of things about this design, and also that it conforms with Major League Baseball rules. So Aaron can tell us more about that when he joins us. This is just at the very beginning of the season. The torpedo bat users had higher batting average, higher on-base plus slugging percentage, and higher average exit velocity by a couple of miles per hour. That's the rule book. Okay. We can talk about aluminum bats afterwards. I'm just going to finish for a couple minutes telling you that technology is providing data that are changing the game. And the coaches know how to use those data. I'm going to tell you where they come from. There's a set of very fast, high frame per second cameras, 12 of them in every Major League Baseball park. By Hawkeye Technology, you can get analysis of all the data they produce in this baseball savant, and I made this table, and then some of the data that I have. You can get all sorts of stuff. You can figure out what pitches it is. And what's remarkable to me is the camera can also track points on a batter, joint points, and a runner around the stadium. And I guess give you stuff like that. So that's the technology. So anyway, the science of baseball is incredibly rich. Not anyway, but wow. Fascinating, amazing. It's changing the sport. It's a fun way to teach physics. I hope you learned a little bit of physics, and also how physicists approach thinking about very complicated situations with just enough to understand what's going on. And of course, there's much, much more. So my final comment is play ball. Thanks.
All right, so we'll take just a minute. Those who need to leave should feel free to head out now. Otherwise, we'll have a Q&A with Tim Chupp, and hopefully we'll have Aaron Lienhardt online with us as well. And those online can email their questions to physics@umich.edu. And those in the room will have microphones available to ask directly.
Go ahead and try to join the Zoom. Ah, excellent. All right, Aaron is known as Lenny these days. And you have questions for me, you could have questions for Aaron. We don't see you, but I think that's fine. Let's see if we can hear you. Say hi, Aaron, Lenny. Uh-oh.
How are we doing now, Tim?
Okay, that's good. I can hear you, and we have the tech.
Got me?
Yes, one moment. Awesome. Let's see if we can get this into the room. Or I'll have to borrow a microphone.
That one should work if you turn it on and turn the little That's, no. Christine, do you have? We'll correct that one. I thought you were using this.
And we'll just get the hand mic. Okay. Sorry, Lenny. I think, go ahead and say hello again. Thanks so much for joining us. I hope the lecture was okay and there weren't too many errors in what I said. There's a long line of people here who want to ask questions, so let's start.
Sure. Thanks for the lecture, Tim and Lenny. I'm curious, you mentioned the torpedo bat making a big splash in the news at the beginning, and I was waiting for you to say whether it fell off or not. I haven't heard as much about it. Did it fall off, and if so, why? Did pitching change? What happened through the season? Thank you.
Okay, we lost him. All right, while we wait for him to come back, and this is untested, this is a first for Saturday morning physics, though we're going to try to do it again in the spring. Oh, he's back. Okay. I'm going to repeat a question, Lenny, that we just got about the sort of essentially the statistics on the use of the torpedo bat and whether it fell off or just left the headlines, and what impact it's had on the Major League Baseball season.
Well, that one was for me there.
Could you hear that question?
Yeah.
Okay.
I heard parts of it. You're just asking about how the torpedo bat actually performed this year and the statistics on it. Is that correct?
Yes.
Yeah, so I think I cut in and out there a little bit. I think the initial outburst of home run was probably like a over dramatization for maybe the upside of a particular piece of technology. I think something like torpedo bat is the kind of thing where over the course of the season, it's going to make you marginally better on pretty much every single swing you take. And when you integrate that over 162 games, you're going to see the results work out in your favor on any one play, any one swing, any one event. It's going to be maybe hard to attribute credit or penalty. Oh, I see the video's finally working now. Credit or penalty to the bat per se. But I do think over the course of the season, you're going to see contact rates go up and the quality of the batted balls in play go up a little bit as well. But it's probably going to take a full season of using it before you can really say that you personally saw a positive impact or not from it.
About how many players do you know used it regularly?
I think that's a fair question. I think lots of guys try it. They switch between bats all the time. My guess would be when all things kind of shook out, probably close to 15-20% of the league might be using it regularly. I think this offseason will be a big offseason for guys to try to see if they can get a bat fit to their liking. Mid-season adjustments tend to be a little bit tougher for players. So the players that came in prepared to start swinging the new equipment this year were probably the ones that stuck with it throughout the season. And this had actually been a project that had been in the works for over 3 years now. So I think a lot of people behind the scenes had been tweaking these bats to their liking, and really the rest of the league is probably going to play catch up this offseason to it.
Okay, another question.
So when they pitch the ball, it goes really fast. So do you like wear anything to protect you? And what happens if you get hit? Has anyone gotten hit by the ball?
Okay, so the question was, when a batter gets hit by a pitch, what happens most of the time, and yeah, how do you coach that?
So when you get hit by a pitch, you get first base. It's meant to be a penalty for the pitcher and sort of a reward for the hitter, if you will. Generally speaking, nowadays there can be a lot of injuries when that happens. The pitchers are throwing pretty hard, and the hitters have started to wear elbow guards and things like that, hand guards, to protect themselves from the bones that are most likely to get broken when they get hit. Generally speaking, we don't do a lot of coaching on that other than to basically tell the guys to swing at strikes when they're over the plate and take balls when they're off the plate. If the ball happens to hit them, then they just go ahead and take first base.
While we're waiting for the next question, I just wanted to ask about the ball coming back towards the pitcher. How often is that a real danger?
Yeah, thankfully not very often. When it happens, it definitely everyone notices it, right? If a pitcher ends up taking a line drive off the chest or off the head, it's a very scary moment. Probably gets hit near the pitcher fairly hard. A few times a season. Usually they're able to deflect it, with their own glove and things like that. Occasionally, unfortunately, they're not able to, and then they can, certainly sustain injuries that way. Probably, once every few years, you see a major injury at the Major League Baseball level.
And no online questions at the moment.
Next question.
I would think the sweet spot would be the end of the bat. Why is the sweet spot not the end of the bat? Because the bat would be going faster,
right,
farther out from the hand.
So I'll take that real quick, and then Lenny can add. So the sweet spot is the place where the most energy of the ball-bat collision goes to the exit velocity of the ball. Contributes to the exit velocity of the ball. At the end of the bat, these vibrations of the bat are excited much more easily. Even though that's moving a little bit faster, it's true.
The end of the bat would be faster.
Correct.
Hitting the ball.
So there's an advantage. It's moving a little faster, and there's a penalty for the energy that doesn't go into the ball. And the sweet spot wins. Would you like to add anything?
Yeah, Tim, I think you showed a really great video of that effect, right? When the ball was shot, the bat vibrated violently like a wave, and it snaps at the handle. So it is true. Oftentimes, the end of the bat is going to be moving faster than the points closer to the handle. But the vibration of the bats is probably the single most important thing for the exit velo of the ball. So it's a really big deal that you do not excite the vibrations of the bat. If you excite the vibrations of the bat, that's all energy that's lost in the collision, and none of that energy goes into the exit velo of the baseball. So the real thought process behind the torpedo bat was to recognize that the vibrational modes of like a free beam, which is basically what a bat is, pretty much set the sweet spot in the same location for all bats. It's about 6 to 7 inches down from the tip, and so the whole goal was to put as much wood as possible in that area, with the understanding that you still had to leave a little bit out there on the tip, otherwise the vibrational modes shift too far in as well. So that was really what the trick was behind the whole design process, and ultimately that's the region in which you'll always have the highest exit velocity, regardless of the fact that certain parts of the bat are actually moving a little faster than the others.
That's very cool. Did you use finite element methods to design this?
I would like to say yes. I think we did something about very similar to what you were doing there, hanging a bat from a string and bouncing a baseball off of it, and just showing, figuring out where sweet spot was. That was more of a way to convince the players where they should have the most meat on the bone, so to speak, where they should put the most wood. We actually have data that just pretty much tells us where the players hit the ball the hardest, and it's very tightly clustered in a range from between 4 to 9 inches from the tip. It's kind of like a Gaussian histogram, like you might expect. So generally speaking, you're only going to hit a ball, let's say over 100 miles an hour, if you're hitting it somewhere between 4 to 9 inches from the tip, with the hardest ones typically being hit centered, between 6 to 7 inches from the tip.
So that's effective physics. Next question.
It's a pretty commonly observed phenomenon that if you hit a ball down either foul line, it'll curve more foul. So how is it that depending on where in your swing path you hit the ball, you get the opposite side spin on the ball?
So the question, if you may have caught it, but I'll just repeat it, is that foul balls near the foul line, tend to curve away from the field, whether they're going left or right, and actually probably whether they're pulled or a late swing. Can you explain that?
Yeah, it's a very good observation, and it's definitely true. The reason tends to be when you pull the ball in the first place, that usually means you're kind of out and around it. So you kind of hit a little bit on the outside edge of the ball in order to pull it. And then when you hit on the outside edge of the ball, that also creates the appropriate side spin to make it continue to hook and go foul even more. Whereas when you hit the ball the other way, that usually means you hit it on the inside edge of the ball, which now you stayed inside the ball a little bit, and that means it tends to go the other way, but it also slices a little bit more also. So in other words, when you hit the inside of the ball and you push it to the opposite field, that also gives it the correct side spin to keep slicing away, more foul. So it just tends to be the nature of whatever bat path you take that generates a pull or generates a hit to the opposite field. Also generates the type of side spin that causes it to continue to move in that direction. That's actually a very good insight for our outfielders, because the left fielder and the right fielder pretty much need to know that any ball hit at them is going to move towards the line. And ironically, center fielders, balls hit straight to center field tend to slice a little bit away from them. The balls that travel the straightest are the ones that are usually hit in the pull side gap. So a right-handed hitter that hits a ball to, say, left center, that's the one that usually goes perfectly straight. It's just something that we train our outfielders to know about, just simply because sometimes they have to take their eyes off the ball and run to where they think the ball's going to be, and this just gives them a little bit better advice on where to target their direction.
Next question.
Hey, Lenny, good to see you. So the question is each hitter has their own swing dynamics. Is each torpedo bat tailored for each hitter, or are they pretty much all the same?
Yeah, that's a good question. So there's kind of two processes involved. The process that Tim explained is really the physical process, the physics behind a free vibrating beam. And that's the zeroth order process, right? The zeroth order process says, because of the way the bat vibrates, the generic sweet spot is somewhere between this window of 4 to 9 inches. On top of that, you have individual hitters that will then have a little bit of a different batted ball profile, a little bit of a different set of swing dynamics, and it's very much what we would call bat fitting, which is very close to what they do in golf and tennis, where they fit your golf clubs, fit your tennis rackets to your individual swing. Because of how you fire your particular muscles, there is a little bit of an advantage or disadvantage to moving some of the weight around to tailor it to your swing. So I'm kind of punching here on a specific answer, but basically telling you it's both. You try to optimize putting the weight where the vibrational modes are going to be minimum, and then you try to move it around a little bit to fit your particular swing as best I can.
Any online questions? Okay. Next question.
This is maybe a somewhat related question, but if everyone were to adopt this bat, I'm wondering, would the Ohtanis and Judges disproportionately benefit from it, or would the weaker hitters who generally don't have the greatest contact, would it be more of an equalizing technology within the league?
Oh, that's a great question. Probably a bit of an open question right now in the industry. The first answer I gave, I I'm fairly confident in, which is probably the case, that over the course of a season, everyone's going to have some benefit from it. The reality is, certain hitters that maybe have wild misses that chase a lot, they might benefit from it a little bit less, because they're really just kind of either going to square a ball up or miss by a mile. Maybe some of the hitters that tend to have a lot more batted balls on the bat to begin with are the ones that are going to benefit a little bit more from it, because each one of those is going to play a little bit better. So I do think that's something where the industry is trying to actually sort out right now who might benefit the most from it. And it's probably just going to be an empirical answer, to be honest. I think over the course of this offseason, lots of guys are going to get fitted in a way they can get a bat that's tailored to their swings, kind of like the last question alluded to. And a lot of guys will probably go into next season with something that's probably a little bit designed better from a physics standpoint, where more of the meat's on the sweet spot, but also from a personal standpoint where the bat has been tailored to their swing a little bit better. And we'll probably have a little more information to answer the question this time next year.
I'm going to ask a question. I hope I don't take it away from either of you, but do you think that as this changes the game, even incrementally, new bats, that's going to change pitchers' approaches?
I think what we see is all these incremental adjustments. They take a few years to build up, and then the other side reacts to it, right? So over time, pitching has kind of incrementally gotten better and better, and this might be one of the many ways and hitters are reacting to it. So over the next couple of years, as hitters start to develop maybe better swing mechanics or better technology in the bats they're swinging, pitchers will then try to find ways to counter that adjustment as well. So those kind of incremental adjustments tend to take, let's say, 2 to 3, maybe even 5 years to settle in, and then the opposing side makes their adjustment back. So the game does tend to meander rather slowly when it comes to these things.
What do you think of Cal Raleigh, and how much do you think his improvement this year is potentially due to the torpedo bat?
I just want you to know that's a Mariners fan asking that question.
I can tell. I'm never going to take credit away from any of these guys. They've got to be the one that stands in the box. And as Tim did a great job of explaining to you guys today, they've got less than a half second to figure out what they're doing and put the barrel on the ball. It's an impossible task. My role is just to help make that impossible task a little bit more possible. He obviously did a great job this year swinging it. The bat probably helps everyone a little bit, whether that means it helped them with, 1 homer, 6 homers, a dozen homers, who really knows? But, credit to him for getting it done this year, for having the courage to make this adjustment actually mid-season or early in the season. Happy for him and the success he had. There's actually a lot of interesting stories behind those Rawlings bats that Tim held up, the Cal Raleigh model. If you squint on there, I'm not sure the one that Tim has the model number on it, but if you squint and you look at the model number on the one that Cal is swinging, it's got someone else's initials and number on it. So really, it's credit to those players that helped design those things originally, and then just a lot of other players have kind of adjusted them and kind of made adaptations to them to suit their needs. So it's been a long process, and those guys really deserve all the credit and all the success they've had from swinging them.
Has there been a switch hitter who hit 60 home runs before?
I think he did set the record. I think Mickey Mantle had the previous mark, maybe low mid-50s, 54, something around there.
Right. Next question.
So you showed all these slow motion videos of like a slider and a fastball and how the spin causes it to bend one way or another. Could you talk a bit more about how a knuckleball does what it does?
Oh gosh. The question's about knuckleballs, and I didn't actually brush up on the knuckleball for this presentation. It was on my list, but to be quite frank, I had to be game ready. So, do you have a specific question about knuckleballs?
Just how the aerodynamics of it interact.
Right. Well, I can refer you, I'm going to, of course, defer to Lenny here in a minute, but I can refer you to a few articles on the research on knuckleballs. But of course, they don't work very much like the pitches I discussed, where there's aerodynamic forces are so dominant because of the spin, right? Obviously, the air and the stitches on the ball that's really not rotating much at all have a lot to do with the surprising motions that it makes. Beyond that, I don't have a lot to say. What would you like to add, Lenny, about knuckleballs?
Yeah, honestly, I'm thankful that most pitchers can't throw them because they're very difficult to hit for all those reasons. And I grew up as a hitting coach. I think I will defer you to some really cool stuff that's been done recently, and you can find a lot of it online. I think there's a website called Baseball Aerodynamics. It's a research website run by a group at the University of Utah, and they've actually been studying a lot of the qualities of laminar flow and turbulent flow around a baseball. And they've actually discovered a lot of the physics that's been taking place in the game for a long time, even related to spinning objects. And it's very interesting how the seams and how the seams are rough parts on the baseball and how the smoother patches actually interact with the air. And pitchers have gotten so good now, they can actually orientate how the seams rotate through the air to actually modify how the ball moves through the air because of this sort of like disconnect between the laminar flow and the turbulent flow around a baseball. It's actually a really interesting question. It's why golf balls have dimples, for example. You think a sphere is a nice round smooth object. It turns out a golf ball without dimples does not get hit as far as a golf ball with dimples because of all these kind of issues with laminar flow and turbulent flow around the ball. And so the seams on a baseball actually help it maintain a little bit of turbulent flow and help the air stick to the side of the baseball that moves around it. But pitchers are now finding ways to cause that flow to break off in a way that all of a sudden causes the ball to jet in a sideways direction very violently. And so to some extent, your knuckleball question is a little bit related to all of that stuff, which is basically, how the air interacts with the baseball. And so in the case of a knuckleball, the air interacts differently because the spin is so low. And in the case of some of these other pitches where the spin is very high, you can actually still cause the air to interact with the baseball in a different way if you orientate the smooth patches and the rough patches on the baseball in a very particular manner. So this is kind of probably leading edge, if you will, research and pitch design right now at all levels of baseball. And you can definitely read about it online here at the University of Utah website. I think it's called baseballaerodynamics.com.
One thing I didn't mention about the spinning ball is that the spin axis is relatively stable, because when something spins, that's why we can ride a bicycle, right? It wants to maintain its axis. I just realized that's something I left out of the complication of spinning balls. All right, we're getting short on time, but we have, I think, at least one last question here. Go ahead.
Are there any drawbacks to the torpedo bat? Is it heavier in any way, or?
So the question was, are there drawbacks? Is it heavier?
Yes, about the torpedo bat?
About the torpedo bat, yes.
Everything?
Yeah.
Yeah. So that is probably where we did the most research, and I wouldn't really call it. I mean, finite element analysis is probably what we did. We didn't really study vibrational modes per se using that technique. We mostly studied the various moments of inertia. So the center of mass, the moment of inertia, the higher moments of inertia, to basically make sure we knew what the length, the weight, and the weight distribution was. So to some extent, that was part of the bat fitting process that we did. We really wanted the bat to have the same feel in the player's hands. But how do you quantify feel for a player? In like kind of layman's terms, it's something that they call swing weight. And in physical terms, it's basically like a moment of inertia, not just how heavy the bat is, but how that weight's distributed. Is it end-loaded? Is more of the weight closer to the tip? Or is it more balanced? Is more of the weight closer to the hand? So we actually did a lot of analysis on that when designing the bats, to make sure that at the end of the day, the player would almost close their eyes and be able to swing their current bat along with a bat that we designed for them with a torpedo shape, and actually still have kind of the same feel, same swing weight when they swung it. There's no reason why you have to maintain that. back to the point of one of the previous questions, there may be a better weight distribution for any individual swing. And there's definitely ways to fit players to sort of the correct weight and weight, linked weight and weight distribution for their swing. We just kind of took the bat they were currently comfortable with and made the assumption that somehow they had implicitly fit that to their swing already. That's not necessarily the right assumption, but that's the assumption we started with to get the project off the ground. And that's part of the reason why I'm suspecting that this offseason people will probably dig in a little bit deeper and do a better job of merging both things, kind of the physics of the shape of the torpedo bat along with the actual bat fitting process, and probably find a lot more guys coming into spring training next year with bats that are kind of tailored to their needs.
Great.
All right, that concludes our Q&A. Thank you so much for coming, and thanks once again to our speaker, Professor Tim Chupp.
Thanks so much, Lenny. Let's thank Lenny also.
Yes.
Professor there, and appreciate all you guys missing the opening kickoff here for the football game to stick around for this. Thank you all.
Yes, and thank you, and we'll see you in 2 weeks where Ann Curzan will be giving our talk on language and science. So thanks, everybody, and thanks, Lenny. I'll be in touch with you. Or you can stay.